Artificial intelligence has become a cornerstone of contemporary technology, powering everything from search engines to financial forecasts. But how are AI models actually trained? This documentary will unravel the processes and techniques behind the training of AI models, offering an in-depth look for tech professionals seeking clarity and advanced understanding. At the surface, training an AI model is about teaching a machine to recognize patterns in data. It starts with raw data input: images, text, audio, or numerical information. The goal is to create a system that can generalize from examples and make intelligent decisions about new, unseen data. The journey begins with data collection. For high-performing AI, vast amounts of high-quality data are essential. Teams painstakingly source, clean, and annotate datasets, ensuring consistent standards. The more representative and diverse the dataset, the better the AI can perform across real-world scenarios. Next, the data undergoes preprocessing. This involves normalization, dealing with missing values, encoding categorical variables, and sometimes augmentation, particularly with images or text. Proper preprocessing eliminates biases and errors that could undermine the training process. Choosing the right model architecture is pivotal. Neural networks, especially deep learning models, have gained prominence for their ability to capture complex relationships in data. Researchers decide on the number of layers, nodes, and connections, tailoring the architecture for the specific problem. Initialization of model weights comes before training. Weights are random values assigned to connections in the neural network. Strategic initialization, such as He or Xavier methods, facilitates stable learning and mitigates issues like vanishing or exploding gradients. With architecture and data ready, training begins. The principle is simple. The model iteratively predicts outcomes, compares them to actual labels, and adjusts itself using feedback. This feedback loop is orchestrated by the loss function, which quantifies prediction errors. A loss function, such as cross-entropy or mean-squared error, computes discrepancies between model predictions and true values. The aim is to minimize the loss, transforming the AI from an untrained novice into an expert capable of accurate predictions. Backpropagation is the backbone of model training. It calculates gradients, indicating which weights need adjustment. By propagating the loss backward through the network, backpropagation enables the model to learn the optimal way to tweak its parameters. Optimization algorithms execute these updates. Stochastic gradient descent, ASGD, remains the industry standard, but variants like ADAM, RMS-prop, and AdaGrad offer improvements by adapting learning rates and accelerating convergence for complex models. Learning rates must be carefully set. If too high, the model overshoots minima. If too low, training becomes inefficient. Advanced techniques like learning rate schedules or warm restarts dynamically adjust learning rates for optimal progress. Batching strategies manage the data flow during training. Full batch processes are rare due to memory constraints. Mini-batch updates strike a balance between stability and efficiency, typically processing 32, 64, or 128 samples at a time. Epochs define the number of passes the model makes over the entire data. Higher epochs enable deeper learning but risk overfitting, where the model memorizes training data rather than generalizing. Early stopping ensures training halts once optimal performance is reached. Overfitting prevention is crucial. Techniques like dropout randomly deactivate neurons during training, preventing the network from becoming excessively reliant on specific paths. Regularization methods, such as L1 and L2 penalties, further restrain model complexity. Hyperparameter tuning is an iterative, data-driven process. Parameters like batch size, learning rate, number of layers, and activation functions are systematically adjusted using grid search, random search, or Bayesian optimization for best performance. Validation sets are used to monitor training. After each epoch, model performance is evaluated on unseen validation data. Consistent validation accuracy signals effective learning. Drops or stagnation may indicate overfitting or underlying dataset issues. Data leakage is a subtle but disastrous pitfall. When training and validation sets are improperly separated, the model inadvertently learns patterns from the validation data, leading to inflated performance metrics and poor real-world results. Transfer learning accelerates progress for domains with limited data. Pre-trained models, such as ResNet or BERT, are repurposed by fine-tuning their parameters on new, domain-specific data, leveraging prior learning for rapid improvement. Distributed training has revolutionized scalability. By partitioning data and computation across multiple GPUs or machines, massive models, like those used in natural language processing, can be trained efficiently, reducing time from weeks to days or hours. Gradient accumulation offers a compromise for memory-limited environments. Gradients are aggregated over multiple mini-batches before updating weights, allowing larger effective batch sizes without exceeding hardware constraints. Mixed precision training uses lower precision arithmetic, typically float 16 instead of float 32, reducing memory usage and boosting throughput. Careful scaling maintains accuracy, balancing the trade-off between speed and statistical integrity. Model checkpoints safeguard progress. At critical intervals, model states are saved, enabling training to resume after interruptions and facilitating rollback to earlier configurations in case of degradation or overfitting. Debugging and diagnostics are routine. Visualization tools like TensorBoard, coupled with custom logging, allow engineers to track loss curves, accuracy, and parameter gradients in real time, surfacing anomalies before they become costly errors. Curriculum learning structures the data flow, presenting easier examples first. The model builds confidence and gradually encounters more challenging samples, mirroring human pedagogical strategies and improving convergence rates for complex tasks. Warm-up phases gently ramp up learning rates in early epochs, avoiding abrupt jumps that destabilize training. Gradually increasing intensity ensures the model finds its footing, leading to smoother and more effective optimization. Synthetic data generation is sometimes necessary. When real-world data is scarce or sensitive, generative adversarial networks, GANs, or simulation tools build artificial datasets, expanding training possibilities while preserving privacy or rare event diversity. Ensemble methods combine multiple models. By aggregating predictions, ensembles reduce variance and boost robustness, often outperforming single architectures, especially in high-stakes applications like credit scoring or medical diagnosis. Adversarial training bolsters defense. Injecting crafted adversarial examples during training forces models to contend with edge cases and malicious inputs, improving resilience and reliability in safety-critical environments. Once training is complete, evaluation is exhaustive. Model performance is rigorously tested against validation and test sets, checked for metrics like accuracy, precision, recall, and F1 score. Only the most robust models earn deployment.